Alright, so we defined ring homomorphisms, so we need to talk about the ring homomorphism theorems. So basically I'm just going to state them, and I'm not going to prove them, because the proofs are almost identical to the proofs that you have for the case of groups. Because what's going to happen is if you look at these, basically what's happening is every time you just talk about subgroups, in the group isomorphism theorems, you just well, obviously you're going to replace group with ring when you go from group isomorphism theorems to ring isomorphism theorems. You're also going to take, whenever you see a subgroup, you're going to replace it with subring, and whenever you see normal subgroup, you're going to replace it with ideal, because remember those are the corresponding kernels of homomorphisms. So basically, what we're doing here is just that. So I don't know what these are. I feel like I'm missing one. Nope. Oh yeah, I miss it. Okay, because I always think there's like 3 isomorphism theorems, but the first one is typically like the fundamental theorem of group homomorphisms or ring homomorphisms or whatever. And so sometimes they're included and sometimes they're considered their own separate thing. What my current professor does is he calls this isomorphism theorem number 0 and then this number 1 and this number 2, which goes back to the whole like, oh, natural numbers include 0 thing, which I guess algebraists really like to do. But I'm going to start at 1, so this will be 1, this will be 2, this will be 3. Anyway, so the first one is just the same thing we have before. If you have a ring homomorphism and you take the kernel, then there is a unique map from the quotient into the ring such that the map can be written as the composition of this map with the projection. And so like this arrow thingy here means that this is surjective, because certainly if you're projecting onto a quotient space, then that's going to be surjective. And then this map turns out to be injective. And so you basically, you take F and you write it as like a composition of a surjective map and then an injective map. And of course, what else do you have? If F happens to be surjective, then you can prove that that F bar is an isomorphism. Right. So there's that, and then, or certainly you can prove that F is an isomorphism if you just consider the image of F here. All right. So there's that one. You know, I've seen these discussed so many times, and I've literally never seen a proof. Let's see here, I've had 2 separate classes now in which I've seen these theorems presented. In both classes, they just said, oh, it's just like the group homomorphism theorems. So, and then I read Jacobson, and Jacobson also says, oh, you can prove these just like you prove the group homomorphisms. I wonder if anyone has ever proven these isomorphism theorems, or if everyone just knows that they could do it and doesn't do them, and therefore no one has done them. So who knows? But so that's the first one, and you prove it somehow. For the second one, what we have is if you take an ideal and you consider, we're going to use R bar to be the quotient. And remember, quotients for rings are with respect to the additive operation. So now we have a one-to-one correspondence between subgroups of R plus, and I made sure to specify it here, that this is subgroups with respect to addition. So additive subgroups. So well, I guess that's sort of forced, because it can't possibly be a subgroup of the multiplicative group, because multiplication is not going to be a group. It's going to be a monoid. So subgroups of R containing a one-to-one correspondence to subgroups of R bar. And of course, R bar is the quotient. And the map is given by, you take an ideal, or you take a subgroup. Why do we call this I? I don't know. But you take I and you map it to I bar. So you basically just quotient it. So everything in here looks like a quotient of a thing in here, and everything that's a quotient of a thing in here looks like this. And now, just like in the Now, in the case of groups, obviously these two things were subgroups, but here we have the additional thing that if I happens to be a subring here, in addition to being an additive subgroup, if it's also a subring, then I bar is also a subring. And so that's sort of an additional thing that we get here, but that's not hard to prove. And then the other thing is that if I is an ideal, well, I is an ideal if and only if I bar is an ideal. These are both if and only if statements. So something in here is an ideal if and only if it's an ideal in here. All right, and if I happens to be an ideal, then we can take this quotient, which we can do because we can only take quotients with ideals. But anyway, so we take this quotient and it ends up being isomorphic to this quotient here. And of course, since this is an ideal, we know from this that this is basically all the preliminaries, all the stuff that comes before this verifies that this is something that you're allowed to write. So yeah, we have this isomorphism here, and then the last one is if you have a ring with a subring and an ideal. So remember, when the group case, you just had like a group G and a subgroup H and a normal subgroup K. Here we have a ring R and a subgroup S and an ideal A. Then S plus A is a subring of R, which contains A. Right, so this is a subring. And S plus A, if you quotient by A, then that's isomorphic to S quotiented by the intersection of S with A. And let's see here. The intersection of ideals is an ideal, and that should be easy to prove. Because let's say we've got fancy A and fancy B are ideals. Then if you consider their intersection, both of these are additive subgroups of R, and so we know that the intersection of subgroups are subgroups, and so the intersection of these two is going to be an additive subgroup. And then if we take something in their intersection, R times C, where C is taken from fancy A intersect fancy B, well, since A is an ideal, this is going to be in R times. So this is R times A, so it's something of the form R times A. So then because fancy A is an ideal, this is going to be in A. And since fancy B is an ideal, this is going to be in B, so it's going to be in the intersection. Okay, cool. And then therefore the intersection of ideals is an ideal. Okay, cool. So then yeah, so you get this quotient. So this is an ideal, and it's a it's an ideal of S. Because it's an ideal of R, and S is a subring of R, and so in particular it's an ideal of S. And certainly this is contained in here. Alright, so that's all good. Now let's talk about modules for some reason. I'm not quite sure why we threw this in here, because modules are sort of their own thing, and we don't really talk about them yet. We wait a little bit before we talk about them. Yeah, so I think this is a little strange organization to define modules here. But, I mean, we might as well. I mean, I got nothing else to do right now other than define what a module is. And we could always just come back to this when we actually start to talk about modules in depth. And I think part of the reason might be is that, like, this is sort of, it's sort of a separate, when you learn about them for the first time, it feels like it's a separate thing in ring theory. Like, it's sort of like like vector spaces are their own thing, groups are their own thing, rings are their own thing. It feels at first sort of like modules should be their own separate thing, but they're really not, because really what a module is it's the equivalent of what a group action was, but in the topic of rings, because basically what this is if you have a ring, a left R module is an abelian group M. So we'll say we have a left R module M. So this is an abelian group, and we will denote its law of composition by addition because it's abelian. And we also have this map from R time R, the direct product of R with M into M. So basically what this should remind you of is this should remind you of group actions where we had a map from G cross X into X, where X was a set. And I think this is sort of why this might be why we bring it up now, because when we talked about group theory, I think we brought up group actions early on. But then, of course, in that case, we proceeded to talk about group actions a lot after defining it. Here we're not going to. Here we're going to bring these up and then leave them. So, yeah, whatever. But yeah, so the main point here is that here in group theory we had a group acting on a set. So we had, and this is sort of a natural way to think about a group, because you could think about a group as like actual like rotations and symmetries of some set of things. And so this was sort of an interesting way to think about groups, is not just groups in and of themselves, but as things that do things to other things. So here, this group G is something that does something to X. So we have this map from G cross X into X, and there's some other structure there. So here what we're doing is we have additional structure on our ring R, and so we can't, I guess you could define a ring acting on a set. I don't know how you would do it, and if you did find a way to do it, I don't know if you would get anything interesting. But it seems like people realize that if you let this ring act on an abelian group, then things work a little better, and you can do a lot. So the only difference is we place groups with rings, and we replace sets with abelian groups. So anyways, so a left R module is an abelian group M and a map from R cross M to M, such that if you're given, so there's a couple things that go into it. We have a lot of structure on this map here. So if you take an R and R, then this gives us some. If you fix R, okay, so if you fix R, and then think of this as a map from M to M given by sending M to R times M, where here, this will be, if we take R comma M, this will get sent to R dot M. So when I do this dot means that we're taking, this is sort of R acting on M. This is sort of like the dot is sort of referring to this map here. So this dot means R is acting on M. So if you fix an R and consider the map that sends M to R acting on M, then this is a homomorphism of abelian groups. So of course here we have addition in M, and here we have this is mapping into M, so this is also addition in M. All right, and then, so now if we rewrite this map, instead of thinking it like here, we thought of it as you fix an element of R and you get a map from M to M. Here we'll fix an element of, here what we do is, well, this is the same exact, this is sort of the same thing. But here, we're thinking of this from M to M, and here we're thinking of this as a map from that goes from R to group homomorphisms from M to M, given by you send the element R to the element of group endomorphisms of M, the map here which sends M to the action of R on M, where R dot M, of course, is given by this thing again. And this is just a rewriting of this. So anyways, this has to be a ring homomorphism. And again, ring homomorphisms, we had three things. We needed it to work under addition, multiplication, and the multiplicative identity. So this is more of like a higher level abstract way of defining modules. So let's sort of write out these things, what they literally mean, to get more of like something you can sort of get your hands on and actually work on exercises with. Okay, so we know that this is a homomorphism of abelian groups. So what that means is that if you take M1 plus M2 here, then R acting on M1 plus M2, it should be a homomorphism. So basically what that means here is that if you have R acting on M1 plus M2, then this is going to break into the sum. You take R acting on M1 and then you add R acting on M2. And of course here both of these additions take place in M. Alright, so this is what we get from this map being a homomorphism of abelian groups. Because you fix, because what you do is you take M1 plus M2, and then of course when you act on this you're going to get R acting on M1 plus M2, but if you were to act on it separately you'd get R acting on M1 and you get R acting on M2, and you want adding these together to be the same thing. So yeah, so that's exactly this thing here. So because that's repetitiously redundant to have it in twice, I will remove it. So we have this, and now we get three things from this map being a ring homomorphism. So for addition, so if you add two things in here, so if we take R1 plus R2 here, then the map that sends M to R1 plus R2 acting on M, that should be the same thing as if you consider the map that sends M to R1 acting on M and just adding R2 acting on M. So it's basically just this. And then the other thing that we have is that if you take so that was taking plus here to plus here. Now we want to take multiplication here to multiplication. So here what we do is we take two elements R1 times R2 and let that act on M. Then that should be the same thing as first acting on M by R2 and then acting by R1. So there's that. And then the final thing is that it should send 1 to 1. So if we consider the identity element here 1, then this should map to the map that fixes everything. So if we think of 1 acting on M as the map that's given by 1 as an element of R, then this map here better fix M, i.e. 1 times M better be M, and this must hold for all M. Alright, so there's that. Alright, so let's take an example. Every abelian group is a Z module. You can prove that. Vector spaces are modules over their respective fields. So that's why this should look a little familiar. Because basically this this map that we're taking here is scalar multiplication, basically. And of course the modules here are that's just addition of vectors. So yeah, so there's that. And then if you well, first of all, you can have R as an R module. If I just say like a Z module or an R module, I mean left module. We'll typically, you have to fix like either, you have to be talking about either left modules or right modules, so we'll typically fix left as what we use. So anyways, you can let R act on this by you take R acting on these by just let it act on each one individually. And here the action becomes multiplication in R. All right, we also got a definition. If we have homomorphisms of R modules, so if you have two modules over the same ring R, then you have a map if it's a homomorphism of the abelian groups, i.e. this, and we also need F acting on R dot M to be R acting on F of M. So this is sort of like pulling a scalar out. So this looks like linearity of a map. So that's again showing like how this looks like vector fields or vector spaces. All right, we'll call the set of such maps Homer M1, M2. Unfortunately, that means that we can't use R to refer to ring homomorphism, so we'll have to find something else for that. But we will worry about that another time.